Hey there! I'm glad to see you here at Devtoberfest. My name is Matthias and I'm leading the engineering team behind SAP HANA's JSON Document Store. And I can tell you that it's an honor for me to have the opportunity to talk to you about one of my favorite topics today. During the next roundabout 25 minutes, I will be introducing you to the basic concepts of the JSON Document Store and highlight the enhancements that have been made after its release with SAP HANA Cloud. As I want to make this a little bit more engaging, I planned a couple of minutes for a system demo, and to round up the presentation, I will slightly shift perspectives and show you how an SAP open source project helps you to seamlessly migrate your MongoDB applications and the JSON document store of SAP HANA Cloud. As this is all pre-recorded, you will have the luxury that my 1 week older alter ego will be answering all your questions live in the chat during the whole event. Let's take a step back and start this from a bird's eye view. The document store is one of the cornerstones of SAP HANA's multi-model engines, which covers all the data that is not relational in nature and may require dedicated processing algorithms. There is a native engine for processing spatial data. It offers a dedicated data type, algorithms, and integration into relevant geographical information systems. There's the graph processing engine, which makes sense out of connected network data. It supports pattern matching queries with OpenCipher, as well as the implementation of own advanced algorithms in a language called GraphScript. And last but not least, there's the JSON Document Store, which we will cover in more detail today. Our goal for those multi-model engines is to make them a first-class citizen next to relational data. We aim to provide all multi-model functionalities on the SQL layer, rather than having specific API protocols. We want our users to be able to work seamlessly across all engines, and we want to provide domain-specific access to different personas. For the data scientist, we offer a Python interface. Developers can reuse built-in algorithms, and many domain-specific software packages offer connectivity to SAP HANA already. Now we will leave the bird's eye view and dive into the JSON document store itself. What the JSON Document Store delivers at its core is a native ACID-compliant storage for JSON documents, or more broadly, semi-structured data, which may, for example, contain arrays, objects, key-value pairs, and several nesting levels. Typical use cases for working with semi-structured data are product catalogs, sensor readings, or user profiles. Depending on its kind, a product may have very different attributes. For a washing machine, you may want to store the capacity, whereas this attribute has no relevance for a book, where the number of pages may be more interesting. If you want to store all your product catalog data in a flat table, you will most likely end up with a very wide and very sparse table. The JSON Document Store provides a more intuitive solution to handle this kind of data, as each JSON document has its own set of attributes. In HANA SQL, you interact with the JSON Document Store and project, filter, and aggregate the data. Also, and this brings us back to our multi-model vision of unifying all data in SAP HANA, you can join documents with relational tables within one transactional domain. Looking at the roadmap for the upcoming year, there are major topics on the horizon. First, being able to build graphs upon JSON documents. So far, our graph engine only works on relational data. However, supporting the JSON Document Store offers new possibilities for conveniently modeling heterogeneous graphs. Second, support for strict mixed schema, which allows to define a partial schema on your JSON collection. If you think of the example of a product catalog, you want to allow arbitrary attributes for all products, but at the same time you want to assure that each and every product has at least an ID and a name. As we already touched upon the use cases for document stores, let me mention 4 specific aspects which may make you want to use the JSON Document Store. First, you require a flexible data model, like in the example of a product catalog. Second, you deal with objects and arrays, which are hard to embed into the relational model. Think of sensor readings, for example. Third, you require a simplified data ingestion and want to avoid fixed schema mapping. Oftentimes, due to web service, you're even in the situation that your data is in JSON format anyhow. Fourth, since the MongoDB service on BTP has been retired, you may want to use the HANA Cloud as a strategic alternative. Now let me show you how basic doc.store queries look and feel. As most basic operation, we may want to create a so-called collection to store JSON documents. A collection within the document store is comparable to a table in the relational store. A collection can keep an arbitrary number of JSON documents, which would correspond to a record or a row in the relational world. And since the attributes are arbitrary, all you really need to give for the create collection statement is the name of the collection. So you don't have to define attributes or columns or schemas. The next statement we want to look at is the insert statement. So the insert statement can be used for inserting a document represented by a JSON string into an existing collection. You see here we have a JSON string with a name and address. The address is nested, so it has street and city, and also it has a state. And we're inserting it with a statement which is very similar to the SQL insert statement for relational tables. For better integration into SQL, the document store also offers a representation as so-called object expression, which again works with the insert statement. Object expressions are embedded into SQL, and attributes are treated as identifiers. So you see the insert statement with the object expression, it looks almost the same. The difference is essentially the quoting. So you see that name, address, street, and city are now SQL identifiers rather than strings. The advantages of having the object expression becomes clear if we look at a basic query using projection, filter, and aggregate. The attributes of the document can be transparently addressed, and the overall query is very close to a relational SQL query. In case a query attribute is not existent within a document, it will simply return null for this individual document. Our example query here projects address.city, and it aggregates all the other documents and counts the number of documents per city for the state of Baden-Württemberg. Now let's look at join across stores. We create a column store table that we would like to join with our customer's collection. So it's the usual create column table statement. We do insert two values for Paul and Mary. The way how this works is by using implicit views, which map the collection to an expected schema that can be joined with a table. Again, if a certain attribute is not existing for all documents within the collection, the document store will compensate this by returning null. The second part of the statement is a regular join with a relational domain. So you see here the with clause in the beginning does the relational mapping of the collections, and afterwards that implicit view is used like a usual SQL view, and you can do the join. What you've seen on SQL level on the last two slides is available on-premise since HANA 2 SPS 03 and in the cloud. However, recent enhancements of the document store have been delivered to SAP HANA Cloud exclusively. First and foremost, due to its close integration into the database core, the document store inherits the enterprise qualities that SAP HANA Cloud is known for. These comprise near-zero downtime upgrades, high availability, backup and recovery, the HANA deployment infrastructure, also supportability aspects, tooling, and many more. From a feature perspective, the document store has significantly matured from its on-premise version. Developers can now use SQL parameters to avoid SQL injections, which has been one of the most frequently asked features for the on-premise version. We have added full support for JSON arrays. As an example, arrays can be unnested and filtered with dedicated predicates. Both JSON representations, JSON string and JSON object expressions can be used equivalently when writing any SQL statement. On top, we have reworked the internal memory management and are continuously investing in performance aspects. I was now mentioning unnesting of arrays a couple of times, and yes, I was not expecting you all to simply know what this is. So let me give you a comprehensive example. Assume we have a collection with two documents. Each document has two attributes, an ID, and one attribute called array, which consequently carries an array as value. We can use the unnest functionality of the document store to transpose these documents into a table, which has one record per ID and array element, which can be used for further aggregates and the like. So you see the example here. We have the two arrays with ID 1 and 2. ID 1 carries array elements 1, 2, 3, 4. ID 2 carries 5, 6, 7, 8. And if we traverse that, we do get a table with, in this case, 8 entries with the corresponding combinations of the attributes. This feature is very powerful when working with arrays, since in that representation you can have filters on individual values, for example. I do have some examples on that slide, also how filters on individual elements can be done more performant than with area unnesting, but to not further bore you out, I will keep this slide for your reference and rather show you the statements in the system. Okay, so now let's get to the fun part and do a little system demo. I'm opening up my database management studio. I've got a HANA Cloud instance here to which I'm talking, and I already uploaded some sensor readings data of the city of Newcastle. So that's essentially air pollution data of different sensors across the city. I have created a collection census data in schema observations. So let's first jump into that schema. And the first thing we may want to do is check table metadata. So when we go to system table tables and search for that collection or collection table called census data in schema name observations, we will find one entry which is a table called census data, and the table type is collection. So don't be misled. A collection is not a table, and also a collection doesn't use the mechanics of table. It has its own persistence, but still it's nicely integrated into the metadata that you have here. On top of the table metadata, we do have some more enhanced metadata specifically for collections in system view collection tables. So if we query that view, we will see that there is a collection or a collection table called census data in schema observations. We see here that it even has a collection ID rather than only the table OID. We see there's an estimated document count of 244, allocated size and used size. Currently the collection is loaded, so these values may differ, like if the collection is not loaded, if it hasn't been used for a time. Also you will see zero values here because it always refers to the loaded data. There is an automatic paging to disk if data is not used. Okay, now we got some enhanced data here. Let's look into the actual JSON documents. So by looking at the top 5 sensor data readings, which are not empty, or let me be more precise, it's not sensor data readings, but it's one JSON document per sensor. So it's 5 sensors. What I mean by that, you see it here in the preview. So if we look at that cell, we go into the JSON preview, you see that it's essentially one sensor here, and there is an attribute called data. In that attribute called data, there is an array called NO in that case, where we have all the measurements of the NO level. So there's always a timestamp, there's a value, there are units. If we scroll further down, so there's also NOx measurements, there are NO2 measurements somewhere, and there's also information for the sensor itself, like the sensor name or even the geospatial location of the sensor. So talking about the geospatial location, let's maybe do something more sophisticated, project out some data in a relational format, and also use our spatial engine to actually map the well-known text that we have here in the JSON representation. So well-known text is a spatial data format, and it's understood by HANA. And you see there's actually a function called stgeom from text, which transfers well-known text into the internal representation. So if you use that to project out some data, you'll see that there are different sensors with different IDs, and they're on different locations across the city, and each sensor has in that example, NO2 measurement. And we can even use that spatial tab here to see how it's distributed across the city. Okay, what we've also done is actually accessing that array via the dot notation. So you see here, or you have seen before, that within the attribute data, there were multiple arrays. There were NO measurements, NOx measurements. We only selected NO2 measurements for our case. Now, one valid question would be how many NO2 measurements are in there per station. For that, we can use the function cardinality and ask for the cardinality of the array, which is the number of measurements or the number of elements in the array. Executing that, we will see that there's some stations with 60 measurements, there's some with 4, so they don't all have the same number of measurements. Here there seems to be even a station which didn't measure any NO2 at all. Now let's go ahead and unnest an array. So again, we take the array, we transpose the data to have really one measurement value per row in the table. For that, we use the unnest statement, and that's the familiar part of the SQL statement, and it's prefixed by unnest data.no2sarr. And ARR is the identifier that can be used in the projection to actually fetch certain values from the array. So it's not a simple array that we have here, it's not just an array of numbers, but it's an array of JSON objects, and that's why I can ask for array.variable, array.value, array.units. So looking at the result, we see that the first air monitor, it had 4 values, if you remember the statement before with the cardinality. And now we see that instead of 1 record for that monitor, we do have 4 records for each individual element in the array, or each individual measurement. We do have the individual measurements here with a timestamp also and with a variable that's been measured. In that case, we only unnested NO2, so we don't expect any other values than NO2 here. Now on top of unnesting, we can use a filter to, for example, ask for outliers and to ask for stations which measured a NO2 value of higher than 130. So we take the same statement, simply append where array.value is larger than 130. And you see that has been 2 stations. So there's one station and here's another station. You see it's almost the same time where the value was exceeded. Maybe they're even in some kind of proximity, but I'm not judging how large the city is, so I can't say anything about proximity here. But it kind of makes sense that when one monitor measures a high outlier, that the other, which is in close proximity, does the same, if it's a real outlier and not caused by the monitor itself. Now what we can additionally do to get the same result is use the for any filter. So here I used first the unnesting, then I filtered with a where condition. Instead of doing that, I can also directly use a where condition and say where for any item in data.no2 satisfies item.value larger than 130. So that has 2 advantages. One is there's no need to unnest the array, which is a costly operation. So from a performance perspective, if I'm simply interested in the outlier detection, the for any filter is preferable over first unnesting then filtering. The other advantage, think of the situation that there is a station which reports over a period of time consistently a value larger than 130. For the first unnesting query, it would be multiple times within the result set because it would list all the values larger 130. With the for any query, it's simply interested if there's any item in there which is larger 130. So if one of the values exceeds the value, I would just get back the station once instead of multiple times. Good. And now the last statement. And the last statement is a bit of a mind twist because actually what we can do is that we even combine unnesting and the for any predicate. Why do we want to do that? In that specific query, we are interested in all the measurements values of the stations which at least one time exceed the value of 130. So we're first filtering where for any item in data NO2 satisfies item value 130. And then we're unnesting. Or you can also see the other way around. We unnest and then filter all the JSON documents which satisfy that condition. So what we will get now is 2 stations, but for the 2 stations we will get all the measurement values. So that's what you see here. You get station 760 150, and if we scroll down, it's 759 150. So it's the 2 stations. But in the result set, they're all the measurement values, the ones above 130 and the ones below. This concludes our demo of the JSON Document Store. You've seen some simple queries, unnesting of arrays, and complex filtering based on arrays. I hope, like all the theory that we've seen before on the slides, now got a bit more tangible for you, and you know how it feels to actually talk to the document store with a SQL layer. I will now switch perspective from an internal to the more external view. As mentioned, our goal is to integrate our multimodal feature set into the SQL layer. However, there are existing applications out there which do use specialized APIs, with the MongoDB Wire Protocol being one of the most common. To enable a smooth migration of legacy applications towards the SAP HANA Document Store, we have started an SAP open source project called the SAP HANA Compatibility Layer for the MongoDB Wire Protocol. The project essentially has been forked from FerretDB, which is an open source project that at that time pursued the same goal, but with a Postgres database as a backend. What it ultimately does is mimicking the MongoDB Wire Protocol and internally translating the requests into document store queries. The result is again returned by the Wire Protocol API. The database used in the backend is transferred to the driver or application that has been built on top of the Wire Protocol. The project is functional and available on GitHub. Existing MongoDB drivers like the MongoDB shell work with SAP HANA by using the compatibility layer. We can quickly have a look at the GitHub repository, and what you will see here is actually, if you scroll down, that there is a basic tutorial, like quick setup, which helps to get you started, how you install the middleware, and how you actually talk to HANA with the Wire Protocol. You also have a paragraph up here for known differences, because in specific, sometimes different values are returned than from MongoDB, which means migrating an existing MongoDB application to SAP HANA is smooth, but still needs some work, which is probably not surprising. Looking into the future, FerretDB has slightly changed its course and is opening up the original project to support multiple backends, other than only Postgres. As we talk here, we're working on an integration into the FerretDB project, so keep an eye on that in the future. With that, you've gotten a high-level overview of the document store and also recent enhancement that's been made over the last 2 years. You've seen a demo, you've heard about the compatibility layer for the MongoDB Wire Protocol. But on another note, Devtoberfest historically appears to be the warm-up for TechEd. I will give you a couple of recommendations which sessions should not be missed if you happen to attend either virtual or in person. So here are my 2 TechEd sessions to watch out for. First is a virtual session, a virtual jumpstart session. It's DA285V, named Building Intelligent Data Applications with SAP HANA Cloud. In that session, the document store will be featured together with also graph processing capabilities, the spatial engine, and machine learning embedded into the database. You will learn how to build the next generation of solutions on your database. The second recommendation is a lecture on-site in Bangalore, which is called Generative AI powered by SAP HANA Cloud. You will learn about recent enhancements in the multimodal space with regards to generative AI, and I'm sure there will be surprising news out there. So if you happen to be in Bangalore, join that session. With that, we are through our presentation today. I hope my 1-week-old alter ego managed to answer all your questions in the chat. If not, or if possible, I will stay around as long as possible, so don't stop asking questions, just continue. If there are still questions open afterwards, or you would like to have a follow-up discussion, feel free to reach out via either LinkedIn or the social network formerly known as Twitter. Thank you, and have a good day, everyone.